Hello, everyone. My name is Bryan Wilder, and I'm a PhD student at Harvard University. This talk is on AI for population health, melding data and algorithms on networks. The high-level motivation for my work is that public health is one of the big challenges facing our world, accounting for a majority of premature deaths worldwide. And this is particularly the case in low-resource settings where many people lack access to essential care. But as the COVID-19 pandemic demonstrates, infectious diseases are really everyone's problem. Accordingly, my work is motivated by the drive to build AI, which can impact population health problems. And this requires us to bring together a variety of tools and areas, being able to understand data via machine learning models, use that to drive decision-making via optimization, and to do both of these in the context of the social networks and structures that underlie population-level dynamics, things like behavior change and disease transmission. Accordingly, the technical focus of my work is on how we can design systems which span this entire pipeline from data to deployment. And this includes the process of gathering potentially costly data, using machine learning to build predictive models, using those predictive models in optimization to allocate scarce resources, and then actually deploying the resulting systems in the real world where they can have an impact. And so over the course of my PhD, I've worked on a range of themes across this pipeline, including algorithms for sampling and gathering information on social networks, techniques to integrate together machine learning and discrete optimization, and optimization algorithms which are robust to the uncertainties generated by this process. Along the way, I've also had the opportunity to collaborate with a range of amazing experts in domains including childhood obesity, HIV prevention, tuberculosis, and most recently, COVID-19. And through these partnerships, we've been able to create systems that have had real impact. This includes a project on HIV prevention, where the AI-augmented methods that we developed resulted in a field trial that enrolled over 700 youth in total and showed significant improvement in key risk behaviors. Other projects include an ongoing partnership with the city of Mumbai focused on tuberculosis treatment, where we're using data from thousands of real patients to build predictive models for medication adherence and to optimize follow-up interventions by health workers. And finally, most recently in response to the COVID-19 pandemic, I worked closely with epidemiological collaborators to build tools rooted in modeling and statistical inference. And one key output of these collaborations has been to help provide evidence in favor of rapid testing policies, resulting in widespread media coverage and helping support our epidemiological collaborators as they push for policy changes. In this talk, I'm going to focus on the first of these projects, dealing with HIV prevention. And I'll start out by motivating the problem, then provide an example of one of the technical problems that our approaches had to deal with in this domain, and then finally cover the real-world deployment and evaluation of the resulting system. So the context for this project is that homeless youth face sky-high rates of HIV prevalence, about 10 times that of the general population. Accordingly, drop-in centers and other organizations that work with homeless youth will conduct educational interventions where they try to raise awareness about HIV and about prevention strategies. And they do this by training a small number of youth to be peer leaders, hoping that these youth will be able to disseminate the message to others through their social network. That raises a computational problem, often referred to as influence maximization. The idea here is that we're given as input a graph which represents the social connections between people in a population. And then we'd like to select a limited group of up to k seed nodes from the graph to disseminate information as widely as possible. There's a great deal of previous work in the computer science literature on algorithms for influence maximization, but by and large, this previous work assumes that the graph is known exactly, that someone tells us precisely who is connected to who, and the probability that information will diffuse across all of these edges. Of course, in the real world, especially in a setting like community health, none of that information is available. Accordingly, over the last several years, I've worked together with social work partners to develop and deploy an AI-augmented intervention that we call Change. And this system was deployed in a trial enrolling 700 youth over the course of 2 years, providing the first deployment of AI methods for social network interventions in health. Now I'm going to provide an example of one of the key technical challenges that we faced in designing this system, which relates to the lack of data about the structure of the social network. By and large, previous algorithms for influence maximization assume that someone gives us the entire graph as input, tells us exactly who's connected to who. But that data, in fact, has to be gathered from scratch, and it requires really costly face-to-face interviews that pose a key bottleneck to being able to scale up these interventions in practice. This raises a new computational question of whether we can subsample the network. Can we query just a limited number of nodes to find out who they're connected to, and use that information to nevertheless reconstruct an approximately optimal set of influencers? Unfortunately, we can show that in general the answer is no. There's no silver bullet solution in the sense that there exist graphs where any algorithm with a constant approximation ratio has to query nearly all of the nodes in the network. But this isn't the end of the road, because we know that real networks often have significantly more structure. And one really common example of this is community structure, where nodes are grouped into distinct subgroups, and there are much denser connections within these communities than between them. One common way of formalizing this in the literature is what's called the stochastic block model, which is a probabilistic model over networks. And the idea here is that nodes within a given community are connected with some probability A, nodes in different communities are connected with some probability B, and A is significantly larger than B, leading to the emergence of distinct communities. So now I'm going to present an algorithm for sampling networks, which is motivated by this kind of community structure. And then I'm going to argue that this algorithm is a good idea by showing a theoretical analysis of it on graphs that are drawn from the stochastic block model. The algorithm works as follows. So suppose that we have a network which looks something like this, but we don't know anything about the structure of the network to start with. So we're just going to query a uniformly random node on the network and ask them who they're connected to. From there, we can start to simulate a random walk, moving to one of their neighbors, and so on, building up a little local picture of what this community looks like. And we can do this multiple times, choosing new random starting points and simulating more random walks, iteratively building up these many little local views into communities on the network. And so the focus of the theoretical analysis of this algorithm is to show that this kind of sampling scheme gives us enough information to find influential nodes using only a few samples. And the intuition here is that for graphs with significant community structure, a good approximation to the optimum is to seed the largest K communities, where K is the total budget. And so when we try to look for these large communities, a really useful property is that the average degree in a community scales with that community's size. And this falls out of the stochastic block model theoretically, because any pair of nodes in a given community are connected with some fixed probability. But this is also something that we observe out in the real world on networks gathered from homogeneous populations. As a result, we get this really useful property that information we can observe locally, i.e. the degree of the nodes that we encounter on this random walk, is informative about global properties, right? The size of the community that these nodes are embedded into. Accordingly, we can use the following algorithm. We can start by running a polylogarithmic number of random walks, each of which goes for a polylogarithmic number of steps. And these parameters are chosen to ensure that we hit every sufficiently large community in the network with at least one of these random walks. And then each walk has enough time to mix within its own community, right, to give us a representative sample of the nodes. And then using that information, we can estimate the largest K communities in the network by looking at the average degrees and construct a randomized sampling scheme to hit the largest K communities, each with at least constant probability. The end result is the following theoretical guarantee, that this algorithm obtains a constant approximation to the global full information optimum using only a polylogarithmic number of queries when graphs are drawn from the stochastic block model. And this is really encouraging because it means that by leveraging the kind of structure that we see in real networks, we can in fact get an exponential improvement over exhaustive sampling, i.e. just querying all of the nodes. But this is still not the end of the road because we know that real networks have properties beyond community structure. And so over the course of this project, I worked to develop a larger system to systematically optimize the choice of seed nodes on the sampled subgraph. And this is the system that we call change. I'm not going to go into any additional technical detail, but roughly the idea is to first gather a subgraph of the network using the mechanism that I just showed you. And then we designed robust optimization algorithms to optimize the choice of seed nodes on the network while accounting for uncertainty about how information will propagate and potential contingencies, like some nodes not showing up to attempt the intervention. For now, though, I'm going to switch over to the actual deployment and evaluation of these methods in the real world. And this was a project that came together in partnership with 3 Los Angeles area drop-in centers working with homeless youth and with collaborators in the USC School of Social Work. In this trial, we compared 3 different arms. The first was the change system that I just illustrated. The second is the status quo method in public health, degree centrality, i.e. just selecting the most popular youth from the population to be the seed nodes. And then the third group was a control group that was only observed. And so the key result from this trial is as follows. We surveyed youth to find out the fraction of them that were engaged in unprotected sex, which is one of the key risk behaviors for HIV. And what we found is that in groups that received the intervention planned by change, there were significant drops in this percentage over the course of the intervention, decreases of about 30 to 50% in total. And by comparison, in groups that received the intervention planned with degree centrality, there was no real change over time. And what this tells us is that correctly targeting the intervention, which the AI-based methods allowed us to do, is really the make or break issue to get this program to work in practice. But more broadly, I think that the lessons that we learned over the course of this project point a way forward towards an agenda for AI centered on the needs of communities around us. Because really pulling together this project required very close engagement with the surrounding community. It required us to spend a lot of time at drop-in centers for homeless youth, engaging with social workers, with the leaders of the centers, to build the kind of engagement and trust that this project required. And moreover, that engagement was crucial to reveal new technical challenges and chart out a broader theoretical agenda, for example, highlighting the role of data limitations and how we should design algorithms in these settings. And ultimately, I think that if we embrace this kind of feedback loop between technical progress and close engagement with the people around us, that ultimately as AI researchers, we have a big opportunity to create broader coalitions and help create change in our own communities. And so with that, thank you very much, and I'm happy to answer any questions.